Hi, and welcome to this section of the Physics Tutor where we're going to expand our discussion of collisions. Specifically, we're going to talk about the different types of collisions in physics, work some problems, and we're going to also talk about the special case of a collision when it's a little bit more complicated and you have a collision at an angle. So one of the balls comes in at some kind of an angle, okay? Now, the main thing that I want to impress upon you here before we even get to any of the equations is that all of the problems that you deal with in physics at this level when you're working these problems, the momentum is going to be conserved in all of these problems. In other words, the total momentum before and after the collision is going to be the same. And we've talked about that in the previous lesson. I'm going to reinforce that here by writing some stuff on the board, but just kind of keep that in the back of your mind. The momentum of all the particles added together before the collision is going to equal the momentum of all of the particles after the collision. So that's pretty important. Now you're also going to come across some terms that I'm going to define on the board that are going to further describe this collision, and some of these terms are called an elastic collision and an inelastic collision and a perfectly elastic collision. The perfectly inelastic collision and things of this nature, okay? And so the big picture here is just think of all of those classes. In all of them, the momentum of the system is always conserved. So just commit that to memory. Hey, momentum is always going to be a constant before and after the collision. So that part's pretty easy, okay? Now, when we start getting into the elasticity, the inelastic or elastic nature of the collision, simple thing to remember is in a perfect system, like with billiard balls, perfectly hard, solid balls that hit each other, they don't kind of flex whenever they hit each other. They're totally hard and they're rigid, okay? When they hit each other, that's called an elastic collision. And that means that in addition to the fact that the momentum is conserved, the kinetic energy is also conserved in the collision, okay? So remember we talked about the conservation of kinetic energy. Well, if you add up the kinetic energy of all the particles before the collision, they're going to interact, and then the kinetic energy before and after the collision is going to be the same. Now, the difference is when you get to these special cases called inelastic collisions, okay? And an inelastic collision, it's like a rubber tennis ball or a rubber ball or something like that that flexes. If you have two of these things that hit each other, they're going to flex when they hit each other, right? Some of the energy that they had initially is not going to be transferred to the other ball. Some of that energy is going to be absorbed in the deformation. So the bottom line is in those cases when you have any kind of a ball that flexes, or anytime two objects stick together and they don't rigidly bounce off of each other like a billiard ball, it's going to be an inelastic collision, and the kinetic energy from the outside point of view is not going to be conserved, okay, in those cases. So, big picture, and I'm going to reinforce this here, but big picture, the momentum is conserved always. And an elastic collision, the kinetic energy is also conserved. In an inelastic collision, the kinetic energy is not conserved. And so keep that in mind as we write some of the stuff on the board. So I'm going to reinforce that here by saying if you have what we call an elastic collision, okay, what that means is that the momentum P and the kinetic energy are both conserved. And conserved is just another fancy word that means it's constant before and after the collision. Okay? So an example of this would be like billiard balls, which would be like a ball that doesn't deform, it doesn't change its shape when it hits each other. It's just a rigid ball that hit and they bounce off, okay? So the momentum and the kinetic energy are both conserved, okay? So what does that mean in terms of physics? How can you apply this to your problems? That would mean that as far as the momentum goes, okay, what you would have for two balls that interact, you'd have the mass of the first ball times the velocity of the first ball, initial velocity, plus the mass of the second ball times the velocity of the second ball, okay, like this, the initial. This is the momentum of the first ball plus the momentum of the second ball is going to equal simply the momentum of the second ball, okay, like this. Okay, this is the momentum after the collision of the first ball and the momentum after the collision of the second ball. Okay, so just think of it this way. total momentum before the collision, total momentum after the collision. This is the momentum of ball A, ball B, ball A, ball B, and this is everything before the collision, everything after the collision. So this is the conservation of momentum, okay? And this will apply to an elastic collision, okay? And also, because the kinetic energy is conserved, you're going to have something very similar. It's going to be 1/2, whoops, mass times velocity squared, 1/2 mv squared. That's the kinetic energy of that guy. 1/2. This is the kinetic energy of the second ball, initial. That's what the I means here. This is the kinetic energy of the first ball after the collision. And this is the kinetic energy of the second ball after the collision. So we have two very, very similar equations. This is the conservation of momentum. This is the conservation of kinetic energy. This simply means the kinetic energy before the collision. If you add the kinetic energies of the two balls up, the initial, that's what the I means, the initial kinetic energy before the collision, and then you add the kinetic energies of the balls up after the collision, you're going to get that. Okay? Now let's compare that with what we're going to call an inelastic collision, which I already hinted to. An inelastic collision is a collision when the kinetic energy is not conserved, okay? Because an inelastic collision is one of these cases when the ball flexes. So the kinetic energy, that these two balls coming together, when one hits the other, it flexes, and some of that kinetic energy of the initial ball, it gets absorbed into this deformation. It goes into deforming the ball, right? So because of that, if you measure the velocities on the outside world, since some of the energy went into deforming the ball, well then the exit velocities of everything flying apart, they're not going to really add up in the right way, okay? So measuring the velocities on the outside is not going to lead to the conservation of kinetic energy. So for an inelastic collision, all you're going to have is this guy right here. And so just to write it over, you're going to have the momentum of the first ball, the momentum of the second ball, and then after the collision, you're going to have the same thing as we had up here. So this is exactly the same thing copied over. So you see these equations really aren't that terribly crazy here, okay? This is the conservation of momentum, this is the conservation of momentum. The only thing you need to realize is for an inelastic collision, a collision when the balls flex, or if the problem simply tells you inelastic collision, you're going to apply the conservation of momentum, which I already told you is always going to be true, but you will not be able to apply this formula because, as we said, some of that kinetic energy went into deforming the ball and doesn't necessarily go into showing you the velocities of the balls as they fly apart.